Welcome back to another AP Pre-Calc video. I'm Mr. Hibble. Today we're looking at 3.10. This is all about inverse trig functions. This is one thing where a lot of people's brains start to get a little bit twisted, a little bit tangled as they're going through these problems because the thought process is a little bit weirder. So we're going to start to break this stuff down and really start to understand it. Few things that we might just recap real quick about inverse trig or just inverse functions in general. Remember, a function and an inverse function, when you plug one into the other, you're just going to get out the value of x. We know that the domain and range for a function and the inverse function always just switch. Third bullet point there says the graph of f and f inverse are reflections over y equals x. Remember, y equals x is this line down the middle. So they're just reflected over that. That's similar to our property for number 1 there. Number 4 here says if a function y equals f of x has an inverse, we get x equals that, right? So we switch the x and the y is what we say. But then we always solve for y, and we can always put it into our function notation to show the inverse there. Okay, we'll look at all of this different stuff at some point, either in this video or the next video. So trig functions are really weird because if you want to talk about a function for an inverse trig, you need to restrict the domain in order for it to work. The reason for that is if you use a horizontal line test. Notice this pink line on this first graph. Okay, there's my horizontal line. If I have that horizontal line and it crosses my function multiple times, it does not pass the horizontal line test. And what that means is this function does not have an inverse function. So, in order to make it so the inverse is an actual function, we're going to restrict its domain at a certain spot. Well, we want to restrict sign so that we get the entire range of values. For example, we want to make sure that we have the values from -1 all the way up to +1. Well, in order to do that, we could restrict the domain at -pi-halves over 2 pi-halves. That's where we get this second image here. Okay? This image then allows us to find the original function. This is the original sine function where the domain is -pi-halves to pi-halves. Okay, and the range, look at the bottom to the top there, is -1 to 1. Well, if you were to take the inverse of that, one of our properties stated that the domain and the range switch. So this is the original with the restriction to allow for us to have an inverse, or an inverse function at least. Well, the inverse, notice here's the inverse function in blue. Notice how we denote an inverse. An inverse for trig functions is shown with that little -1 right after whatever the function is. Okay, this means inverse for these. Well, okay, knowing that then, the inverse, though, we said just switches the domain and the range. So the range now for our inverse function would be -pi-halves to pi-halves. And the domain now has the restriction of -1 to 1. Notice you can also see that in the image. Cosine and tangent have very similar things happening. Notice we need to restrict cosine differently because if I restricted it from -pi to pi, my function only goes from 0 all the way up here to 1. And I don't want that. I want the entire range of -1 to 1. So we restrict it at 0 and pi instead. So the original function then has a domain for cosine of 0 to pi. Its range is the same as the last, -1 to 1. But then if we look at the inverse now, okay, this is the inverse like we were talking about before, those domains and ranges switch. So the range in this case is 0 to pi. The domain in this case is -1 to 1. Same idea for tangent. The domain and range switch. Tangent, we can reduce it or restrict it from -pi halves to pi halves for the domain. But notice this function, the range now for our function, this looks like it's going up forever, this looks like it's going down forever, is all real numbers. So there's the original. The inverse then of this, the domain would be all real numbers now, and the range in this case would be -pi halves to pi halves. Okay, so just some things to note there when we restrict our domain and range. Well, knowing that stuff, let's go ahead and start to play around with these other things. Let's go ahead, let's look at graphing these different functions. Well, we're given the parent function. For example, this graph right now, maybe let's say it's f of x is sine inverse of x, right? And that graph matched the one we saw earlier on that last slide. Well, now what happens is there's some transformations that happen to this function. One thing that happens to this function is it goes down by pi units, and it has a horizontal stretch of 2. Remember that anything on the inside does the opposite of what we expect. So the first thing I might do is take this function and move it down pi units. So if I look at this coordinate here, it's going to move down to pi. This one here is going to move down pi units and down pi units. It now would look something like this. That is just the down pi part, though. The other thing that needs to happen is this needs to have a horizontal stretch of 2. Well, look at where the values are right now. This is at a value of 1. If I stretch that by 2, it means it's getting multiplied by 2, so it comes out here now. This next one was at a value of 0. Well, 2 times 0 is still 0, so this middle coordinate does not change. But that other coordinate that was at -1 gets multiplied by 2, and now it's at -2. So now our function looks something like this instead. Number 2, similar idea. This one looks like it is going right 1. And now this 2 is on the outside of our function. That must be a vertical stretch where it is stretching 2 units. So if I take this function, move it right 1, it would look something like this. But I need to stretch each of these by 2 in the y direction. Well, this one would be 0 times 2. That's still at 0. This one here would be at a y value of pi halves times 2. That means this one's going to stretch up to pi. This coordinate here is at pi, so we multiply that by 2, and now it is at 2 pi. So now we can stretch this function where each of these get multiplied by 2, now giving us this function instead. Same thing for tan inverse. You can apply similar arguments for that one. Vertical stretch of 3. So pi halves times 3 is 3 pi halves. Negative pi halves times 3 is -3 pi halves. The negative on the inside, that's a flip or a reflection, remember. It's on the inside that affects the x values. In order to flip the x, that would change the y. So it's a flip over the y-axis. So now, flipping each of those values as well would give us something that looks like this. And now we have our images. So one thing we can do is look at different graphs. Another thing we can do, though, is look at solving. So number 10 tells us that we want to find the inverse and list the domain and range for the function. Okay, well, realize we have our function, and we know that this function has this domain. This is the domain of the original. So what we need to do is first start by finding the inverse, is what they said. So remember, to find an inverse, you switch the x and the y. So now our function looks something like this. We need to solve for the y value, so we could add the 3 over. Once we do that, we could divide the 5 over. Realize dividing by 5 is the same thing as multiplying by 1/5. So I'm actually going to write this as 1/5 times x plus 3. The reason for that you will see here in just a moment. Okay, in order to move sign, that's a little bit different because I can't just divide by sign because it's an operator that has some input. So instead, when there's an input inside of it, what you need to do is always take the inverse of it, right? The inverse is what undoes specific parts. So if I take sine inverse on both sides, that gets rid of the sign on the right side and moves it now to the left. So now here is our inverse function. Remember, we like to write inverses with this notation, so we just change it back real quick. Okay, so here is our function. Few things that are happening with this function. We know that there is a horizontal stretch of 5. We know that the plus 3 on the inside also means it is going left 3. So now if I want the domain and range, we need to figure out what those are. Well, realize we were given the domain of the original. Well, if I know the domain of the original, that means we know the range of the inverse. So the range of the inverse must be negative pi halves to pi halves. Well, the domain, if we think back to the beginning of the video, sine. Well, whenever we talk about sine inverse, the domain we said was restricted to -1, 1. Okay, but what we want to do here is that was for sine inverse of x. We have translations. We have transformations happening. One thing that is happening is there is a horizontal stretch of 5, meaning these x values get stretched by 5 units. But that wasn't the only thing. There was also our function getting moved left 3. That means each of these values then need to go down by 3, giving me -8, 2. Now we know the domain. Now we know the range for this function. Let's look at 2 more examples to kind of work through this, think through this idea. We'll come back to 11. Let's start with 12. Again, notice this is the domain for the original, so we do know the range for the inverse already will be 0, pi halves. Okay, let's just get that part out of the way. This is the range of the inverse. So we want to find the inverse of our function. Okay, we have it all set up. We've got the y in this function. We can move the values over. That negative in front, you could divide or multiply by -1, in other words. So I could have -1 in front of all this stuff. Realize I'm having it in factored form like I did the other problem, because that is what the inside of our function needs to look like to talk about these transformations. Now we can get rid of cosine by taking the inverse of it. Now to get rid of the 2, you could divide by 2. That's the same thing as multiplying by 1/2. Notice I multiply by 1/2 to show the transformation that is happening instead. And now we can represent this as our function notation at the end. Cosine, we knew that cosine inverse, right? This is cosine inverse, normally has a domain of -1 to 1. Again, that was from the beginning of the video. We saw that. But let's apply the transformations that are happening. The 1/2 that's in front does not matter for the domain. The 1/2 in front only affects vertically. So, okay, we have two things that are happening. There's a reflection or a flip, and we are going right 4. Well, if I flip this, or if I apply this transformation of -1, that just means both of these values multiply with -1. Well, -1 times -1 gives me +1, and 1 times -1 gives me -1. But remember, your domain and your range always need to be written as the lowest value, then the highest value. So the flip doesn't necessarily change the domain. But what does happen is it goes right 4. We can add 4 to both of these, giving us 3, 5 as the new domain. There's an example for sine and cosine. Last example, let's look at number 11 with tangent. They give us the domain for the original, so that gives us the range of the inverse. Now let's find our function. Let's find the inverse function. Switch theta and y in this case. Notice they are not using an x value. They're using theta instead. Multiply the 2 over. Okay, get rid of tangent or move tangent by taking its inverse. And now we have our function. Let's just put it into our inverse function notation. Okay, so we have this, but let's think about the domain of a tangent function. Remember, at the beginning of the video, we said that tan inverse has a domain that is all real numbers. -infinity to +infinity. Again, if you need to check that, go see the beginning. Well, all that's happening is we are stretching it, right? There is a horizontal stretch of 2. Well, if I stretch infinity by 2 or -infinity by 2, it doesn't change the fact it's infinity. It still is covering all real numbers. The domain in this case, just like it was for tan inverse, is still the same here. It is still all real numbers for this one. Thanks for watching. That is one of our 3.10 videos. This one is about finding inverses. If you need to watch the other one, that will be evaluating inverse trig functions. Thanks for watching.